Hello and welcome to the channel. We've got something exciting going on today. So we have the ARRL's Hands-On Radio Experiments book in front of me here. And this is a great book with a lot of experiments. So I'm going to be pulling some ideas from this book as I go through a series of videos about electronics. So the first experiment is Experiment 1, the Common Emitter Amplifier. And this book does a great job of giving introductory equations and setting up your circuit. But as far as real-world applications, it's missing a few steps and some models. So I wanted to create a video on that and go into a little more detail, as well as kind of talk about BJTs in general. So let's get started with that, and we'll see how to design this. So let's talk a little bit about where you would see a common emitter amplifier. So I have here an audio block diagram, sensor system design, and an RF chain system design. And it's important to note that just because you see it in these diagrams doesn't mean it's the best option, doesn't mean it's the most frequently used in that particular scenario. But since the focus of this video is going to be on BJT common emitter amplifiers, these are just some use case scenarios that I put out there on where you may see them. So the benefits of using a common emitter amplifier are that it has a high voltage gain, it has moderate input impedance and moderate to high output impedance. These can also be configured to use as a logic inverter or even a switching transistor to turn devices on and off. So you have a very small signal that you want to use from an MCU, and you need to turn on a big device with a lot of current, a lot of voltage. You can use a BJT to do this. Now, you don't have to go through the same amount of trouble that we're going to go through and do all the math and calculations if all you want to do is use it as a switching transistor. So we're going to focus on one of the more complicated cases, and that is as an audio amplifier, specifically a preamplifier. And just to note, this is the most common configuration for small signal amplifiers, the common emitter. So let's talk a little bit about bipolar junction transistors, or BJTs. This is commonly what they look like. They can change a little bit, but for most of you, this is what you're going to be working with. And the E stands for emitter, B stands for base, and C stands for collector. Now, how these work, you need to send enough voltage to the base that will turn on the transistor. And once the transistor is on, current will be able to flow from the collector to the emitter. Now, there is another type of BJT, and that configuration is the PNP type, which you can see from the diagram, it's a little bit different. It has the arrow pointed up rather than down. And these work in a similar manner to the NPN type. However, there are some differences. They are not interchangeable. So if you're following along with this video, just be aware we're working with NPN type transistors, and I will give you the model number specifically of what transistor we're using. But just keep in mind, if you switch this out, this is for an NPN type, not a PNP. So another thing we need to talk about are some important variables that come with BJTs, that being beta, VT or thermal voltage, and VBE on. VBE being the voltage between the base and the emitter. And that basically says at what voltage did we turn on the transistor. And that's important to know so that we're not operating the transistor in a weird in-between state, or it's off when we want it to be on. So, and we can get that from the data sheet. And I'll show you more about this here in a second with the curves. So thermal voltage, I'm not going to go too much into detail with that. We're going to stick with anything from 25 to 26 millivolts. And that is actually calculated using Boltzmann constant, the temperature at which the transistor is operating at. So we're not going to go into detail with that. We're just going to assume that it's 26 millivolts. And this is very common. If you're using a non-standard chemistry, maybe the silicone was doped with something else, you may need to adjust that. But for the most part, we're going to use 25, 26 millivolts. And beta, if you look at the data sheet, you won't see a beta value stated in the data sheet. What you'll see instead is HFE. And HFE is very close to being the same thing as beta. So we can use that interchangeably in our system design. to know the characteristics of this BJT. Now, beta as a math formula equals the current through the collector divided by the current through the base. So that can be calculated if you have a curve tracer. All right, so first thing I want to do is test this BJT. This is the 2N3904 NPN style BJT. And the reason I want to run some tests on it is just to show you that every BJT has different characteristics, and they may vary from the data sheet. So we need to take that into consideration when we design these amplifiers. So all you have to do is just insert it into these little holes, click down the levers, go into your waveform software. Make sure you have this little box here checked IB over VBE. And then we're going to run a single curve trace on this. And there's our curves. And if you do the calculation for beta right here, it comes out to 184. Now, if we come over here and look at the data sheet, it says that at about 1 milliamp, we could expect anything between 80 and 300 to be our beta value. And you may wonder, why is that such a large range? You can see here, if we're operating at 100 milliamps, it could be anywhere from 30 to 300, even larger. So it's just important to keep in mind that it's difficult to manufacture BJTs and MOSFETs, and their characteristics can change drastically based on who manufactured it, what temperature it's operating at, etc. So just keep in mind that we need to design around that so that beta doesn't have a huge effect on our system. And we will fix that. This can be done with biasing, so we don't need to worry about it too much. I just wanted to go ahead and point out that in this graph here, we have our collector current, and we have our voltage across the common collector and the emitter. That beta is not necessarily what's shown here on the data sheet. All right, so let's go on to our use case scenario here. We're going to do an audio preamp, and these are just important notes here. We have a small sensor or an instrument tap, such as a mic. It's going to be outputting 50 millivolts RMS. It's important to make that distinction depending on what you're working with. That comes out to 140 millivolts peak to peak, with a source resistance of 2 kiloohms. Now our goal, what we want after we amplify it, is 1 volt RMS, and that comes out to a gain of about -20. And the negative comes from the common emitter being an inverting amplifier. So it will make the input negative. Our next stage load, whatever it's driving, whatever it's connected to, we are going to estimate at 4.7 kiloohms. And this is just taken from some volume pots, maybe some pedals or interfaces. So it's not completely impractical. You could see this. And then our supply voltage, commonly known as VCC, is going to be a positive 12 volts. So why use a common emitter in this case? Number one, we need voltage gain. It's also great we have current gain, so we have more power gain total. If we would have used a common collector or emitter follower, that's what it's more commonly known as, it would only give a 1 times gain, which works as a buffer, awesome, but it doesn't meet our needs of needing a gain. Now, common base loads the source too much, and it has very low input impedance. So we're not going to use that either. The common emitter with a partially bypassed emitter being this lower portion down here, will give us a good settable gain. It will operate in a linear region, which is great for predictability, and then we can bias it in a very stable manner. So we're going to go ahead and work through how to do this. This is just showing you what our end goal is here, and we'll work on this part by part. So if that looks intimidating, don't worry too much about it. And let's talk a little bit about gain. So in circuit design, we work with AV gain or linear gain. And it's important to note this is different than what you're normally used to when you talk about audio gain. So this is combination of V out over V in equals our linear gain. And you can see over here on the left, we have in and out voltages. It's not in decibels. And this is our goal of 20 right along this line. And then we also want a high pass filter so that low frequencies are filtered out. So anything below 20 hertz is going to be attenuated and be reduced in our output. So they will have very little gain, which is great, since low frequencies below 20 usually isn't related to any kind of musical, speech, anything. So in this case, we don't want those. As you can see, the current also has a gain, which is great. So we're going to get gain in both voltage and current in this case. So now I want to take that same, this is the same data here for AV gain in volts. And then I'm going to show you what it looks like in decibels. So here's the formula for decibels. It's a little more complicated than just V out over V in. But you can see in our decibel gain, we're actually up here closer to 30 on this line, not 20. And then I've also called out at about 20 hertz here. It's our X value. We have a 27.2 decibel gain. So again, we have attenuation going on here. We don't want these frequencies in our output, so they will not be magnified nearly as much as the pass band will. And then phase plot may be important to some of you. I'm not going to go into detail with it here, but you can see as our frequency increases, we will get that 180 degree shift as well to invert the output. So let's go ahead and start working on this problem now. So we have a couple options, but as you saw from the curve trace before, we're going to choose our collector current to be 3 milliamps. And that is completely up to you what you want to work with. You can choose whatever you need to, whatever you want to, as long as it's within the datasheet operating parameters. And it's good to not be way on the bottom. It's good to not be way on the maximum. You want to make sure that you have good linearity, which you can tell just from the curve. So our curve came up pretty good, and then it went like this. That was really nice. Some of them, they go more like this. And if you have this big region where it's not linear, that could affect your output significantly. So you can look at the curves. That's usually on the data sheet. I didn't find a data sheet for the specific BJT we're using that gave curves. That's why I went ahead and tested it myself. But 3 milliamps here was one of our good options. So we're going to use that. And we also have a beta value calculated for that as well, which I can show you later how that comes into play. So this right here is just a summary of our goal and source. So we went ahead, we chose our IC, 3 milliamps. Next, choose your output, VC. So our voltage at the current. So our output, we want it to oscillate around the midline of our supply. Now that's important because we have a plus 12 supply. That's DC. And our output cannot go greater or lower than our DC supply. So we're taking a small voltage, we're amplifying it. It can't be greater than our supply voltage or VCC of 12 volts. So if we want to have an equal amplification for the high and low, we need to make sure we're about in the middle. So choose a value VC between 5 and 7. 6 volts is right in the middle. Next, we also need to choose the voltage at the emitter, which is going to be 10% of our supply voltage, or VCC. So 10%, we just moved the decimal place over 1.2 volts. So we have 3 important values chosen here. Now we can actually begin working on this circuit. So first thing we need to do is make sure that the DC turns this BJT on, or our VBE saturation, VBE on. And the data sheet states it's anywhere from 0.65 up to 0.95, 0.85 volts. So we're just going to use 0.7 here. It's good, it's in the middle. We don't have to worry too much about it. We know from the curves exactly what it is, but most of you won't have a curve tester. So we're going to go ahead and just use the data sheet here and say 0.7. It's looking good. We're going to use it. So we need to find our voltage at the base. Voltage at the base, simple potential difference here. We have VE plus VBE, or voltage at the emitter. Let me go ahead and label these here. So voltage at the emitter plus the voltage here between the two is going to equal the voltage at the base. So we chose VE. It's 10% of our 12 volt DC supply. And then VBE we got from our data sheet or the curve diagram, whatever you prefer. And that's going to come out to anything between 1.8 and 1.9. Now we use a range because this is also a range. A lot of the details regarding BJTs are not set in stone. Things change. That's why they give ranges. Don't let it worry you too much. As long as you're within the ranges, you should be fine. So, as a general rule, if we have a large source resistance, such as the 2 kilo ohms that we already have, then we want to make sure that when we use this voltage divider to turn this on, that the current straight down this leg here is much greater than the current going in here. And a decent formula for that is I-div for divider. So our current in our divider is about 5 times the current in the base. So if we go ahead and go through this calculation, we're going to use the beta from the data sheet. In this case, we did calculate it to be, about 150. So we're just going to use the data sheet since you don't have a curve tracer with you, most likely anyway. So it's 80 on the data sheet. I just want to prove that you can use the data sheet to design these. You do not need all this complicated test equipment. And that's a big benefit of how we're designing it. So our current through the divider is going to come out to 1.875 milliamps. Again, we already know what IC is. We know what beta is. Run through the calculation. All right. So now we have that value. We can use that to determine the values for R1 and R2. So R2 is going to be the voltage at the base divided by the current going through. And we know that's a simple Ohm's law. It has to be true because this is ground, so we're at 0 volts here, VB up here. And that comes out to about 9.6 kilo ohms. So there is no 9.6 kilo ohm resistor. We come over, we consult this table. This table is just common resistor values. And we see that 10K is about the closest we can get. So we choose 10K. Again, we're designing, this isn't a math problem, so we have to use realistic real-world values. Now, we need to find R1. R1 is our DC supply minus the voltage at the base. Again, it's just a potential difference from there to there, divided by the current. So the voltage across R1 divided by the current is going to give us R1. Again, just Ohm's law. That comes out to about 54.4 kilo ohms. That is not a real resistor. Now, I wanted to get as close as possible, so I chose to go with 2 resistors, a 47 kilo ohm and a 6.8 kilo ohm that gives 53.8 kilo ohms. So when we see the real physical diagram, it will have 2 resistors for R1 rather than just a single one. And that's just to make this as close as possible. Now you can use 1, get as close as you want. It won't be a huge deal. It will just change your VB a little either direction. Okay, now our next step We're working on the bottom right, or the emitter section of the BJT now. We're going to split the resistance through the emitter down here into a bypassed and a non-bypassed section. So at low frequencies, there is going to be a capacitor right here. At low frequencies, this is what the voltage will see. So the DC section is going to see an open right here. No current will flow. And then these will just be in series and add up to about 360. At high frequencies, there will be a capacitor here. And we all know that capacitors at high frequency act like a closed. So it will bypass this resistor completely. It will go around and only see the small RE value. So let's go ahead and calculate the total we need for this whole section. So that's just going to be the voltage at the emitter, which we already know, 1.2. And then our collector current, 3 milliamps, that comes out to 400 ohms. So this 400 ohms is going to be our RE total. Now, you may wonder, how do we know what to put as our small resistor? How do we know what to put as our large? A decent rule is just to say that it's a magnitude less. So just move the decimal place over 1. And that comes out to about 40 ohms. So find a resistor close to 40 ohms. We get 33 and 47. Those are both fairly close to 40. So let's run a quick calculation to see what these should be. And it's just simple math. You already know this. So take 400, subtract 47, and we get the value for this, our RE bypass section. So I did it for both, and that comes out to 353 or 367. Both of these are not resistances that exist in the real world. So we're just going to choose 360 in this case. So let's move on to RC. So what do we know I've already chosen? IC again, 3 milliamps, VC, 6 volts, mid supply. So we need to calculate what value this resistor will be right here. So using Ohm's law, we know the current, we know the voltage at that section, divide them. RC comes out to 2 kilo ohms. Very simple. We like that. So now this is just an optional check right here. You don't have to do that, but we're just going to check our headroom. So VCE, that's the voltage between this point and this point. We just need to know what that difference is so that we can check our headroom. So if we do VC minus VE, we get 6 volts minus 1.2. VCE is 4.8 volts. That tells us we have great Class A headroom. So this is going to be a Class A amplifier. And that's it for the DC section. All right, now the DC is done, let's talk a little bit more about our AC analysis. Now you might be looking at this diagram thinking, what is that? That's totally different from what we've been working with. Yes, it is. However, this is the AC representation of what's going to happen. So we've already biased everything with our DC source. We don't need to worry about DC anymore. We're going to focus on what happens to the AC signal. And since we're amplifying the AC signal, this is very important to us. So some rules for hybrid pi models are over here. And it's very important to note there's a few different models, but we're going to stick with hybrid pi in this case. Feel free to look some up on your own if you're interested. First thing we're going to do, we zero out our DC sources. Capacitors act as shorts. Inductors, we don't have any in this case, but they act as opens. Ground, of course, stays ground. So if we do that, you can see R1 and R2 both go to a ground. That means that these are in parallel. So we put that in parallel. This is the base, the collector, and the emitter representation. This section right here is all part of the hybrid pi model. So we don't see our pi in our other circuit, but it exists as part of the hybrid pi model. And then this dependent current source over here is represented as beta times the base current, IB, or GM times V pi being from here to here. And GM is the transconductance, which is IC divided by VT, thermal voltage, collector current. It's important to note that's not exactly what it is. It actually comes out to a very small change in the current divided by a small change in the thermal voltage. However, it's very common to approximate it using IC over VT, which we're going to do in this case. And we have established that VT is about 25 millivolts. So we use that, we plug it into our equation. We get 0.121 S. I'm not going to go into the details on that. If you're interested, definitely feel free to look into a more in-depth version of the hybrid pi model. But in the interest of saving time, I'm going to go ahead and let you do that on your own. All right, so R pi equals beta over the transconductance GM. We're using the minimum value from the data sheet, 80, divided by what we just calculated, comes out to about 660 ohms. That means that this representation here, this resistor, is 660 ohms. That's important for our small signal analysis. So now we're going to solve for, let me write that in real quick. We're going to solve for the midband gain. So we have Rn pi, which is part of our pi model, says R pi plus beta plus 1 times Re, which is the small Re, because in the small signal model, we only see the small Re resistor. So, as you can see, we then have Rn. Rn is actually from this point onward. That is going to be in parallel with this whole section. We know that's true. So our linear gain for that section is Rn divided by our source resistance plus Rn. So now we need to work on our stage gain calculation. So RC right here is effective is RC in parallel with RL. So basically we're just combining these two into one resistor that's right here. And that is RC effective. So our stage linear gain is this whole formula right here. And you may have noticed this bottom section right here is exactly what we use for Rn pi up here. And then I wanted you to note our transconductance times R pi equals beta. So we can replace these two with just beta. All right, but that is the actual equation right here. So to get our total linear gain, we're going to take AN times our stage gain. And that's very important. So let's go ahead and do that. We're testing with 33 ohm, a small RE resistor. We run through this calculation and it comes out that we have a linear gain in of 0.548. And that's really important to notice. It's less than 1. All right, if it's less than 1, we are not amplifying anything. We're actually almost halving the signal. And the reason for that is this 2 kilo ohm source resistance. Very important to keep note of that. In most situations, they'll run through the problem. They don't have a source resistance. Your gain works out great. And then in real life, you actually use this. Doesn't work out. In fact, it's actually half. So we'd be getting negative 10 if everything was ideal. We don't want that. So we're taking it into account. We then multiply it by the AV stage or linear stage gain, which is negative 36, and that comes out to negative 19.7. That is very close to our goal of negative 20, and that's using the 33 ohm resistor. So that's great. We want to use that. Went ahead and did the test with 47 ohms. It comes out to negative 16.1. Not good. That's too low. And so as you can see, as we increase the RE resistor, our gain actually goes down. So just keep that in mind in case you want it even more than 20. So let's talk about our high pass filter design now. The gain is split between the input divider and the stage gain. We know that from our calculation we just ran. I also wanted to note these are standard capacitor values right here. So this table is very important. We're in the real world. We can't use whatever capacitance value we come up with, so we need to choose the most realistic component we can put in our circuit. So we're going to calculate our RE capacitor across the 360 or 367 ohm branch of our circuit, and that's that RE branch. So we know, this is a standard formula here, the reactance for a capacitor is 1 over the 2 pi frequency times CE. And that is our negative 3 dB down point. So that's the corner when it starts to round off what's being attenuated on the signal. So we want everything below 20 hertz to be attenuated. So we put 20 hertz in here, 367, 360, we plug that in, and we solve for CE. Now, you may be wondering, why is there a 5 on top of this? It's not in our standard formula. You may not have seen it before. Well, the reason there's a 5 in there is because attenuating the signal looks something like this, and our 3 dB down point is right there. Now, this whole section is still being attenuated, but not very much. So what happens if we actually want some 20 hertz signal in our final amplifier? Well, it's going to be attenuated by 3 decibels. That's quite a bit. You can perceive that with the human ear. So by multiplying by 5, it actually shifts this up just a little bit, and we don't get quite as much attenuation. And the reason that's important is because every time you throw a capacitor in the circuit, you're actually creating another rounded off corner and another rounded off corner. And if 20 hertz is in every single midline here, every time you use one of these high pass filters in the circuit, it will multiply their effects because it's less than 1. So when they're all multiplied, by the time you get to the output, your output signal will be much less than 3 decibels down. So we don't want that. That's why we shift it. So shift it comes out to 108.4 microfarads. We consult our standard value chart. We see 100 is very close, but it's low. We don't want to be low. Again, greater than 108. Next one up is 220. So we're going to choose 220 in our circuit. And that will be the capacitor that bypasses the RE. So it's great. Found that. Now we just need to isolate our AC from the DC sections, which are our coupling capacitors. So we have our formula here. FCN equals 1 over 2 pi. Here's our CN, capacitor in. We're going to be solving for that, our coupling capacitor. And these here are source resistance plus our Rn, which we've already solved for. We run through that calculation. We solve for CN. CN comes into about 1.8 microfarads. Go back to the chart. It's not even on the chart because it's so low. I just chose a chart that had the values that we wanted on it. Next one up, we get 4.7. 4.7 still low. Again, remember, these are going to multiply the effects. We don't want that. So shift up again, 10 microfarads. Better to have too much on the low end since we want that 20 hertz low end than too little. So we size up 10 microfarads. Again, same thing for the out. Run through the calculation. We get our load plus RC. Solve for C out. Comes out to about 1.15, which is fairly close to 1.8 microfarads. Again, we shift that up. We are going to choose 10 microfarads for these input coupling capacitors. And that's it. So we can come back and look at our circuit here. And that's everything. So in this case, we chose 10 UF. Now you may be wondering, why does it say 22? Well, when I ran the simulation through a SPICE model to get our gains down here, which you see, it was 3.8 down, even with increasing everything up to 10. So I went ahead and bumped that up to 22. So in our actual physical model that we do on the breadboard, it will be 22 microfarads. And everything else we've calculated. We know RE, we know this one. We've calculated our bypass capacitor. We did RC, did our voltage divider for R1, R2. Everything looks good. So I'm going to show you what the output looks like now, and that's it. All right, so we've gone through all the calculations we need. So let's actually see this in action. So just a quick overview. We have our source over here on the left. There's a source resistor of 2 kilo ohms. The reason I have that is because I can set my function generator using this Analog Discovery 3 function generator to be 0 internal impedance or 50. So most function generators are 50. Keep that in mind if you're replicating this. So I have a 2 kilo ohm resistor for a source resistance. I have my coupling capacitor here. I have 2 R1 resistors as we calculated and 1 R2 resistor. Got our RC resistor here, 12 volt DC source, and our RE section with the RE bypass. And then our V out with the load. Now keep in mind, do not sample from the bottom of the load for V out. That is connected to ground, so you'll get 0 and be confused for a little bit. All right, so let's take a look at our oscilloscope now. We've got our input probe is channel 1 and our output probe is channel 2. So we have about what we wanted. That's 69 millivolts is our input AC, and we have our output as 1.4-ish, and that's AC as well, and that's amplitude. And that's exactly what we were looking for. So that is great. Everything's working properly. So let's go ahead and check our high pass filter now. So we're going to change. I'll set up 1 kilohertz. Let me just go back real quick and show you guys. Okay, so checking the high pass filter, we were at 10 kilohertz. Now we're at 1 kilohertz. This is the middle of our pass band. So I was a little high to begin with, but just to show you, it still works great. Amplitudes are the same. Great amplification throughout that range. So now we're going to check 20 hertz. All right, we've changed it to 20 hertz. And we can see we get a little bit of a decrease there. So it was 1.4, now we get 1.1, 1.13-ish. So that's good. We have a little bit of a drop, but it's not significant. So now let's drop even farther down to 5 hertz. Come into 5 hertz, significantly dropped. So we've attenuated the signal way more than we were before. Still have our same input. Our output now is a 453 millivolts. So any signal below 20, which was our calculated round off point, 20 hertz, will be attenuated. And that's exactly what we wanted in this high pass filter. So everything's working as expected. I hope you guys had fun. Thanks for sticking with me.